In this session we'll be going over logarithms. The fundamental idea of a logarithm is understanding the relationship between logarithmic form and exponential form. So if we have the logarithm of base b of a equal to x, then that's saying that the base b raised to the power of x equals a. This is the main concept, and it would be very important to memorize this relationship. So if we had the logarithm base 4 of 16, in order to evaluate this expression, you need to be thinking in your head, switching to exponential form. So 4 to what would give me a 16? And that'd be a 2. So this would be equal to 2. If we look at the logarithm base x of 9 equal to 2, and if we want to solve for x, then we're going to switch to exponential form to make it a little bit easier. It's another way of seeing it, and that's saying that what squared would give you a 9, and the answer is 3. If we look at one that's a little bit more difficult, how about the logarithm base 5 of 1 over 125? So 5 raised to what power gives you a 1 over 125? This might not be obvious to see, but one thing that may be a hint is that 5 cubed is 125. But how come it's flipped? Well, how do we flip something? Make it a negative exponent. So notice, if it's 5 to the negative 3, that means it's 1 over 5 to the positive 3, which means it's 1 over 125. So here, this would be equal to negative 3. Now we'll go over some properties of logarithms that help us to solve more complicated equations. The first property that we need to understand, or rule that we need to understand, is that the logarithm of a negative number does not exist. The next property would be that the logarithm with base b of m times n is equal to the logarithm of base b of m plus the logarithm base b of n. The next property is that if we have the logarithm base b of m divided by n, this is equal to the log of base b of m minus the log base b of n. So when we're multiplying two different things, we can split them up and add the logarithms. If we're dividing two different things, we can split them up and subtract. The next one is that if we have the logarithm base b of m raised to a power p, this is equal to p times the logarithm base b of m. So if we had the logarithm of something raised to a power, we can throw that power in front of the logarithm and multiply by it. The next one is if we have the log base b of x, this can be equal to the log of a different base a of x over the log of base a of the original base b. This enables us to change base. The next property is that if we have b to the x equal to b to the y, then we can go ahead and say that this is equivalent to x equals y. Similarly, if we have the logarithm base b of x equal to the logarithm base b of y, this is equivalent to x equal to y. So having that said, it may make more sense to look at some examples where this is applicable. If we look at solving 2 to the x squared minus 2x equals 8, if we need to solve this, we can do it fairly easily by using different properties of logarithms. So notice that 8 can also be written as 2 cubed. If we substitute 2 cubed for 8, we now have 2 to the x squared minus 2x equal to 2 cubed. If we look back to this property, our base for both is 2, so we can go ahead and say that their exponents are equal to each other. So this would then become x squared minus 2x equal to 3. And then we could ultimately just solve for this. And we'd have to either factor or use the quadratic, but we've solved this type of thing before. And then once we got our answers, we'd have to plug them back into the original equation to make sure that they're correct. Now let's take a look at 7 to the x equal to 12. This time we can't change 12 to have a base of 7 and then set their exponents equal to each other. But if we look now, let's say that we take the logarithm of both sides. Now we have the log of 7 to the x equal to log 12. Also, it's good to point out that if we have the logarithm of some number and there's no base shown, then the base is a 10. So again, if there's no base shown, it's assumed that there is a 10 there. So now, from here, if we look at this property right here, we can take this power and throw it out front. So back to here, we can take this power, throw it out front. Now we have x times the log of 7 equal to the log of 12. So x would equal the logarithm of 12 divided by the logarithm of 7. And this would be a problem for a calculator. But that's how you do it. If you didn't have a calculator, you would leave your answer in this form. So let's take a look at another problem. Let's say we have the logarithm of 7 minus x equal to 2. So again, sometimes these are easy to solve if we just switch to exponential form. And remember, if there's no base given, the base is assumed to be a 10. If we switch this, convert it to exponential form, we get 10 squared equals 7 minus x. And now we just need to solve for x. We'll get 100 minus 7 equals negative x. 93 equals negative x, so x equals negative 93. And finally, the last one, if we look at the logarithm of 3 minus 2x equal to the logarithm of x plus 24, and we need to solve for x. Well, again, if we go back and look at our properties, if we look at this one, the logarithm of the same base of something equal to the logarithm of the same base of something, we can just say that whatever we're taking the logarithm of are equal to each other. So here we can essentially think of it as just dropping the logarithms. Now we have 3 minus 2x equals to x plus 24. And now this is a very simple equation to solve. We get negative 21 equal to 3x. That should be a 1. Divide each side by 3. We get x equals negative 7.